Okay, so in our meeting, we talked about how to use simulation to carry out inference for the slope. Now we're going to do a theory-based test. Okay, so one way that you can see how much the slopes are going to vary from sample to sample is to do a simulation. So that's what we saw here. These are the values of the slope that we'd expect to see if there were really no association between X and Y. So in this case, between size and price. But there's also a formula that can tell us how we expect those slopes to vary. So you can see the standard error of the slope, it has to do with the standard error of the residuals. It also has to do with the sample size and the standard deviation of your X variable. So if you were to plug into this formula, I'm not going to have you actually do it because it's pretty gross. So you would get 69.63. And notice that this is the number that's given up here, the standard error for the slope. So the way you can think about what this number is describing is that this gives you the sample to sample variation in the slopes. So basically you're imagining if everybody took their own sample from the same population and everybody calculated a slope, how much variation would we expect to see? You can also think of this as the typical distance between the sample slope, B, and the population slope, beta. So how far off do we expect the sample slope to be from the population slope? Okay, so it's a way of saying how precise is our estimate of the slope. So the test statistic is going to take this into account. So this looks familiar. This is sort of the general form for a test statistic that we've seen before. This is going to be a t statistic, and we've generally seen t statistics when we have quantitative responses, so that's not too surprising. Okay, so our statistic here is just the slope, right? That's what we're using to summarize our sample. Minus the null hypothesis value. This is often 0 because a lot of times we'll be testing the null hypothesis that there's no association between X and Y. And then we divide by the standard error of the slope. Okay, so if I were to plug into this, I can take my slope from up here in the output, 212.74. Sorry about the siren. Minus 0, obviously that doesn't do anything, and then divide by 69.63. So I get a test statistic of 3.055, and you can see that number is up there in the output too. Okay, so we're going to use a t-distribution to decide if this test statistic is big enough to be convincing to us. So we need a theory-based distribution to use here. And remember, the t-distribution has different versions depending on the degrees of freedom. So there's different formulas for the degrees of freedom depending on what type of data that you have. But for regression, it's going to be the sample size minus 1 minus the number, minus the number of predictors you have. Okay, so the predictors, in this case, we're using just one predictor. We're only using size to predict the price. But later we'll see examples where we have more than one predictor. Okay, so here we had 13 houses in this data set. So it's 13 minus 1 minus our one predictor, which is size, and we end up with 11 degrees of freedom. So this picture, this is showing what a t-distribution looks like with 11 degrees of freedom. Basically what this theory-based distribution tells you, this is showing you the values of t that you would expect to get, values of t, when the null hypothesis is true. So basically this is serving the same purpose as the simulation. That was showing you the values of the slope that you'd expect to get when the null is true. This is doing the same sort of thing except in terms of the t statistic. Okay, so we can look at this and see if our t statistic is likely or not. So I'm finding 3.055. And because this is a two-sided test, I'm going to do both sides. So basically you would be shading the area more extreme than your test statistic. So So right away you can see that this is going to be a pretty small p-value, and when you calculate it, it comes out to be a two-sided p-value of 0.0109, and that's where that number comes from up here. Okay, so this is our p-value given in the output. Okay, so that's how you do a theory-based test. So I want you to think a little bit about how all of these pieces are connected. So down here it has some questions about what would happen if you change different aspects. Would your strength of evidence or the evidence of the association be stronger or weaker than before? So go ahead and pause the video, try to answer these 4 questions, and then once you are feeling pretty good about your answers, you can restart it and we'll go over them. All right, so let's go ahead and go over these. So we'll start with the slope. What happens is the slope gets steeper, the evidence of the association gets stronger. So we can just sort of think about this intuitively, that if we have sort of a steep relationship between x and y, that means that a change in x has a big effect on y. That's going to be stronger evidence than one where you have a line that's, pretty flat, pretty close to 0. Another way you can see it is you can look at your t-statistic and notice that as the slope gets bigger, that's in the numerator, your whole t-statistic is going to get bigger, and bigger t-statistics means stronger evidence. As the sample size increases, the evidence of the association again gets stronger. And this is probably not too surprising at this point. We've seen this in lots of different contexts, but you can also see it from the standard error here, right? So as your sample size gets bigger, your standard error gets smaller. That's going to make your whole t-statistic bigger. These last two may be a little bit less intuitive, so we'll think about these a little more closely. What happens as the standard error of the residuals increases? So as the standard error of the residuals increases, your evidence actually gets weaker. It may help to look at a picture to see how this works. So standard error of the residuals, that's basically telling you how much spread you have around the regression line. So here, these two have the same slope, but there's much less spread in the first picture. So when there's less spread, it's easier to see the relationship, right? You have stronger evidence of a relationship in the first picture than you do in the second picture. Okay, and then the last one, what happens as the standard deviation of x increases? So it's the bigger your spread in your x's, generally the stronger the association, or the stronger the evidence of the association. So I actually kind of like to think about this opposite. What happens as you make the standard deviation of x smaller? So let's look at a picture again. So this is showing, a pretty reasonably strong association between x and y, right? It's pretty clear that there's a positive association there. But let's say that we restrict our x's and we only look at the high end of the scale. If I only look at the high end, now I really can't see much of an association at all, right? My evidence of an association has gone way down, and that's going to be generally true. And we can actually see this when we look at the formula for the standard error too. As the standard deviation of x gets bigger, the whole standard error gets smaller, and that makes our whole test statistic bigger.